Okay, folks, welcome back. We're going to get started. This is the course on fundamental principles in Catholic bioethics and Masters of Science in Bioethics at St. Thomas University. We're going into the second lecture. So before moving forward, any questions or comments from the previous lecture or anything in the program? Okay, I emphasize to try to make those summaries as complete as possible, the first lectures, because that's a good investment in time and energy going forward. Okay, so that if you get A+ on those first summaries, then you don't have to do the other ones. I will let you know when I see that you're fully grasping what's going on. Elizabeth, good morning. Okay, no problem, just got started. All right, I had something else pending. Oh yes, so the internship hours going forward, I'm going to ask you please if you can each send me your spreadsheet by Friday midnight, right? So aside from the summaries on Wednesday midnight, if you please send me your internship hours on that spreadsheet every Friday midnight. And that way I can keep an account and see how it's going. In the past, what's happened sometimes is that students delay it. And I know that you have basically until December to complete that, but students sometimes delay those hours. And then the last semester, they feel rushed and don't have enough time with other commitments and so forth to finish them. Remember, it's a total of 150 hours, which is quite a bit, all right? And therefore, I want to see that everyone is pacing themselves. Okay, so by Friday midnight, please send me your spreadsheet updated each week, okay? All right. So, Elizabeth, I don't know, we've talked about your internship. Did we talk about your internship a little bit?
We talked about it a little bit.
All right. Maybe if you have a few minutes at the end, right?
Yes.
Continue. Did I ever send you the spreadsheet, the format with
I remember seeing it on the
time,
screen, but I don't remember sending
date, and hours? It's just an Excel
That's fine.
spreadsheet.
Yep.
All right, we can talk
it.
about it.
Simple enough.
Yep. Try to keep it simple. Okay, so if there are no questions from previous lectures or anything on the program, I'm going to continue. And you notice from the previous lecture that this course really, normally it's at the beginning of the sequence, but because a number of you started really in the fall, then we synergized and double up, as it were, with the cohort that is ending now in May, and did the environmental bioethics course together. And again, that will come up in the normal sequence going forward. So, Elizabeth, so don't worry about it. But you will see that from that environmental bioethics course, a number of things can be applied to this one. But just mentally try to reverse it in the sense that in that environmental bioethics course, we saw application of a number of these principles, all right? But now I'm giving you the foundation, both scientific and theological foundation for some of the stuff that we saw in the environmental bioethics course. All right, now we had also left off with the two, all right, so to recap, just very briefly, we're looking at origins. The question of origins of humanity is a bioethical question also, so it's a scientific question, right? The origin of individual human life and the origin of the species as a whole is certainly a scientific question, right? An empirical question, because we live organically, materially, and there has to be an origin to that life. Organically speaking. And also it is a theological question in the sense that it involves the human conscience, at least from the Judeo-Christian tradition that goes back about 5,000 years total. And it's the basis of Western civilization, where we live and where we grow up. It's also a theological question. And basically we maintain that little saying that it is in the first book of the Bible, the first chapter, the end of the first chapter, that we have been created in God's image, right? God's image, and that has immense implications from there. For example, we deduce a basic principle that is used in human life bioethics and is applied in medicine and research, for example, human subject research, etc. Who can tell me what that basic principle that applies to all humanity, whether they are believers or non-believers? And it's also the basis of law, civil law, by the way, in many ways, right? Sometimes it's such a basic fundamental principle that people forget, and we just kind of take it for granted. It's a word that is invoked a lot across society in many, many different areas of human endeavor. What was the question? Yes, that's all right. You're settling in. Yes, sometimes my questions do get a little convoluted. It's a basic principle that is invoked or used even subconsciously in many endeavors of human life. It applies to scientific, it applies to medicine, for example, the practice of medicine. It applies to research with human subjects, in law, in civil living. Why do we need an IRB, Institutional Review Board, for example, for putting forth research that involves human subjects? What is it?
Ethics.
Yeah, so it involves ethics, of course. It involves ethics. It's an ethical principle, right? And like I say, it's so obvious that people, we cannot take it for granted, but respect for human life. Why should we respect human life? You know, why may we not treat human life like we treat a lizard or a rabbit or even a chimpanzee, which is the closest to us, right? That sometimes research is needed at a chimpanzee before we jump onto human trials, to clinical trials. And why is that? I mean, all nature deserves respect, right? But it doesn't deserve the same type of respect that humans deserve. I mean, for very serious reasons, animals may be sacrificed in the lab when it involves the last, like I'm saying, the last step in trials, say, for example, medical trials, medication, drug trials, or even some kind of surgery, for example, before we jump into human trials. Okay? So respect, and respect for the dignity, we say the dignity of human life, regardless of who the person is, regardless of their age, regardless of their social status, if they're rich or poor, if they're handicapped. In fact, for some groups of society, we place a special emphasis on their respect, precisely because they are somehow weaker than the rest of us and not able or not fully able to advocate for their own respect. Like, for example, handicap, or it could be mentally disabled or challenged, etc., right? And so we advocate on their behalf. And now when you apply that reasoning to human life issues, especially at the beginning of human life, in the womb, at the end of human life, when people become more incapacitated and more dependent on others, think of senile dementia or conditions like that, Alzheimer's, advanced Alzheimer's, right? So we advocate for them, but we have to ground that advocacy on something. It's not that something we pull out of the cloud or out of a hat. It's that fundamental dignity of human life. And there we get into arguments that have no previous reasoning, all right? They appeal to our intuition, for normal human beings. For normal human beings, there's an intuition that human life should be respected. All right, because of an intrinsic dignity. And I try to emphasize that it's not based on whether the state recognizes it or not, whether a committee gives me that dignity. No, because it comes from God. It comes from the Creator. All right, so that's one of the fundamental principles there, and we'll build on that, especially in the summer when we're going to the 2 courses of applied bioethics, the beginning of human life and the end of human life. And so the question of origins is a significant question. It's an important question. When does that human life begin so as to be respected, right? And the origins, we can look at 2 levels, at the individual level of each one of us, and also collectively as the human species. I understand also that the collective origin, right? And by the way, so words in science and in theology, as in every field of human knowledge, we also have to learn certain vocabulary so as to speak and be able to communicate with each other, right? And so there's a vocabulary that is learned. And I tell my students always when we do bioethics, along the way, kind of an added value to these courses is that you pick up a little bit of Latin and Greek along the way, right? And so for people who know Romance languages, like Spanish, Italian, French, Portuguese, or Romanian, right? They kind of have an advantage because those Romance languages are based more directly on Latin and Greek. Anyway, I introduced those terms of phylogenetically and ontogenetically. Ontos meaning the individual human being, right? So ontogenesis is the study of the origin of individual human life, ontogenesis. Whereas phylogenetics is the origin of the species as a whole, the group as a whole. And it's, in fact, that's where we get that large classification of phylum, right? Which you have to be careful. It doesn't apply strictly across the board because here we're talking about the origin of an individual species, the human species. Whereas phylum is a large category, right? That includes, under phylum is class, order, family, genus, and then finally get to species at the very the least inclusive category. Still with me? Yeah, all right. So this question of origins is a significant one, and particularly in bioethics, so that we can speak with competence, as I say. And proposing to you that the evidence that I will give for origins will be from science and faith, both science and faith, all right? So in science, we have 2 big systems, we can call it that for now, or 2 big pillars of science as we know it today, which are going to be evolution and genetics, all right? Those are empirical, quantifiable, measurable, and it has to be based on facts, the material facts, the evidence, right, in front of us. Whereas for the faith component, we also have 2 pillars, right? Those 2 pillars are not based necessarily on the empirical facts of science, because faith is a different discipline, basically theology, and those 2 pillars are going to be Scripture and tradition. Scripture and tradition. So when we look at Scripture, Old Testament and New Testament, there we rescue a tradition, again, that goes back 5,000 years, because that's where the Jewish calendar is today, more or less, all right? I cannot tell you the century or the actual year, but I know that they're in the 5th millennium. That's how far back they trace their origins. So they go back about 3,000 years before Christ. And tradition with a capital T, which is all the writings that have come out, basically in the church and in Christianity in general, and also Judaism, in these millennia that apply to human life and the environment, both. Because many, many different denominations and beliefs have written, meditated and written, spoken about the dignity of human life and the dignity also of the environment, of non-human life. All right, so kind of a recap there. Moving forward now, we'll continue with the thing of origins. I'm going to be focusing mostly in the first half of this course. I'm going to be focusing mostly on the scientific evidence for origins. And by the way, we're looking at phylogenetic origins, in other words, the origin of the human species. Okay, and we're going to bracket the origin of individual human life for the next course, precisely, which is the beginning, the biological issues at the beginning of human life. So we're looking at the species as a whole. The basic question here then is, when did Homo sapiens begin? Okay, in time and place. Oh, so the first half of the course, again, just to recap, is going to be mostly on the scientific evidence, which means that we're going to get in some level of detail into the theory of evolution and also genetics as the mechanism for evolution. And then in the second half, we'll look more at the theological, philosophical, and theological aspects of the origin of the human species. So we'll look at worldviews, how we see, how to conceive the world. Basically, we live in three worlds simultaneously, right? I'll get into that in a minute. Then to recap some origins, including going back to the origin of the universe, trying to pick up on the first origin, the original origin, and moving forward, that's going to be rather quickly. And then also to review very quickly a little bit of physics, chemistry, biology, ecology, and so forth. So we're going to move through fundamental forces in nature, what is meant by organic compounds or molecules, a brief look at the primitive atmosphere, because it's going to help us to establish the origin of life as such, not human life, but life as a whole on Earth. Again, review the concept of species and its applications. We'll focus into the area of the genus Homo, because we share that genus with other species that are not sapiens. But we're the only one, we're the only Homo species that is alive today. But there's ample fossil record of other Homo, they're called hominins, that, or hominini, you want to use a very technical term, that were not sapiens, but were the same genus. So, you know, the percentage homology is beyond 99%, which is what we have with the chimp today. And that diversion happened about 6 million years ago with the chimp, all right? And that's 99% homology, DNA or protein homology. So with these other Homo species, it's much more than 90, it's 99.9 or 99.99% homology. Right? Okay, and then this part of modern history of science is picking up a little bit on Myers chapter 1, which will be mostly the second part of today's lecture. And that was the reading assignment for today. Going forward then. These two worlds, these three worlds that I'm calling, that we live in simultaneously, we're mostly aware of one world, but the other two are there in the background all the time, consistently, okay? And in fact, they are, if you want, more accurate, I don't want to say more real, but more accurate than the middle world that we live in, that we're aware of, rather, that we're aware of, because this middle world really is kind of an approximation. This is what I mean. So Thomas Aquinas, who was a theologian, a Catholic theologian and a Dominican monk in the 13th century, in the High Middle Ages, used to say, there is nothing in the mind that has not come in through the senses. Nothing in the mind that has not come in through the senses. The senses being the external senses in the classical definition of the five senses, right? Which are, what? Who can give me one sense? One external sense. Sight, what else? Another one? Auditory, hearing, smell, taste, and touch, skin, right? Those are the 5 classical senses. And they're called external senses because, not because they're external to us, but because the stimulus is external, right? Because they're very much part of our body. So in that sense, they're internal. They belong to us as the perceptive system, if you will. And the system that is receiving the stimulus, but the stimulus comes from outside. There's also an internal sense that goes by various names, but one of the most common names is the kinesthetic sense, kinesthetic. Let me see if I can cheat into writing. It's not gonna let me write there because I was signed into this Word thing. So what I did was I faked it and used a text message. There we go. So I'm using this as an improvised writing pad. It can be seen there. Probably make it bigger. I move it over. Come on. This is supposed to go there. You go. Oh, here. Give me a minute where I get organized. I thought there was a way of moving this. Oh, well, okay. This one is an internal sense, right? It's dynamic and it's kind of a sense that integrates all the others. But it's internal, it's within, and it's kind of a sense of awareness or not awareness. It's a sense of consciousness or unconsciousness, right? For example, at night, the kinesthetic sense is not, it's not asleep, it's active, but it's active more in the autonomous properties of our body. For example, making sure that respiration and circulation are happening, right? But when we are awake, not sleeping, then the kinesic sense goes kind of into high mode because of consciousness. Now we're conscious and we're integrating the other senses because we're receiving information all the time. It's kind of a bombardment of information, even when we shut our eyes. And just reflecting a little bit on our external senses, back to the external senses, which of the 5 do you think is the most important by way of the amount of information that we receive? That's a real question. Which of the 5 external senses do you think the most important one by way of the amount of information that we receive? Sight, obviously sight, yeah. And in fact, I think it's estimated maybe around 95% of our knowledge comes through sight. Okay, we kind of take it for granted when we open our eyes first thing in the morning and we're just absorbing information all the time. And most of that information goes by the wayside. The mind, the kinesthetic sense kind of dumps it, okay? Because, for example, where's the door to the bathroom? You know, we've seen that so many times that it's kind of automatic. But that is an image. That is a real image. So a lot of information comes through our sight. And you notice that somehow the good Lord gave us through a very slow process of evolution, a curtain to the eyes so that at some point we can shut our eyes, even and remain fully awake and conscious, but close our eyes with our eyelids, right? So it's a great blessing to have eyelids simply because we can shut down the information for a while or we kind of get saturated or overwhelmed. The close second to sight, what do you think it is? Yes, hearing. That one, unfortunately, we cannot shut down. Not much. We can with some devices, you know, some technology and so forth. And also, even if we press on, what is this little thing called on the side of the ear? Sorry? Targus? Targus, yes? Targus. Oh, the targus, this one here? Yeah? Yes? Oh, targus, thank you very much. Okay. So if we press on the targus, on the targi, I guess, the two targi, it can mute it, but I can still hear myself, even if my press hard, a little bit from the inside. So we have, but we have to manipulate it more. It's not as easy as shutting our eyes, right? And the hands continue freely. So, but hearing is also important. Reflecting on the senses a little bit, I want to stay with it for a while. You notice that, so there's one part of our body that has all 5 senses, and it's not the largest part of our body. The head, from the neck up, if we make kind of an anatomical distinction and physiological, from the head, the neck up and the neck down, all right, functionally, which is a function of the other? Is the head as a function of the rest of our body, or is the body as a function of our head? Yes, basically, one way of looking at it functionally is that from the neck down is our support system for the head, for keeping the head alive. Remember when I was doing my first doctorate in Rome on moral theology, my PI, my director there, Klaus Demer, he was a German theologian. He wrote an article once, because at that time, we're talking about the early 90s. The technology had advanced so much that there was a hypothetical possibility of doing head transplants. Now, it sounds like kind of fiction, or maybe there could be, for some people, like a gory factor there. But when you think of a person who is quadriplegic, I know a fellow who sadly fell off a 2nd floor balcony backwards for smoking a cigarette and trying to watch the football game at the same time. Yep. And so he didn't die, but he fell basically on the back of the neck and became a quadriplegic, which means paralyzed from the neck down. But he's fully conscious, the head works fine, you know, he can think perfectly well. But he's been bedridden for 25 years now. And he was about 25 when he fell. So it's pretty tragic. Imagine, hypothetically, for those people now, you take that person, that head, which is fully functional, but cannot move without a lot of people support, okay, and technology. And then the other fellow who was on a motorcycle, basically racing up and down I-95, as they do sometimes in the middle of the night, and got into an accident and flew through the air until he or she landed on, let's say, male, so that we match the sex and gender, fell on his head and had a fatal traumatic head injury. So had instantaneous total brain death. But from the neck down, the body is essentially intact. That is a potential. And he even, beforehand, he even signed his license, his driver's license, as an organ donor, which happens. It does happen. They are the prime, actually, if I'm a little involved in organ donations, those are the prime candidates for organ donation, you know, especially vital organs like the heart and the lungs. So anyway, hypothetically, that body could be a potential transplant for this friend of mine, right? But it wouldn't necessarily be a head transplant, because where's the seat of consciousness? It's in the brain. We can assume it's in the brain, right? Of course, well, it's in the whole body when there is a functioning whole body, but when it's the body, when the function is restricted basically to the brain, like with a quadriplegic, then that's where consciousness is. So it's not really a head transplant, it's a body transplant. It's a full body transplant. And it's a conceptual change, right? But it makes it less Frankenstein-like to have a head transplant or to have a full body transplant. It's the identical operation, it's the identical surgery, but conceptually it's different. You're actually giving a support system to a head that whose body has, for whatever reason, has deteriorated. Okay. So anyway, focusing on the head, we see that the eyes are on the front of the head. very much front, very much on the forward facet of the head. That has anatomical and physiological implications. Contrast our eyes to the eyes of fish, who are also vertebrates, right? But they're totally lateral. So they had advantages and disadvantages. Who has more backward sight or to see kind of what's coming from behind? The fish do. They have a bald spot right directly behind, but they only need to wiggle their head a little bit left and right, which is, by the way they swim, right? They swim by wiggling. So automatically, as they wiggle through the water, they are covering that blind spot with one eye or the other. So functionally, as they are swimming normally, they really have a full range. But that is at the expense, because let's say for the sake of ease and doing the geometry, simplifying the geometry, let's say that the range of each eye is 180 degrees, right? Semicircle, 180 degrees, each eye individually. What does that sacrifice for the fish looking forward? It's 180 degrees and the eyes are lateral, say perpendicular to the body plan. What is compromised is overlap on the front of the fish, overlap on the front. Contrast that with us or mammals in general, but us in particular and primates, because many mammals, you think of dogs, well, they have their eyes kind of to the side also a little bit at an angle and so forth. But us specifically, since we don't really see behind us kind of 180 degrees, you can do that test, you put both hands out and where you see them looking straight forward and then move backwards, and you can see that it's about 180 degrees when those hands disappear, more or less. It's still looking forward, right? Do that experiment, about 180 degrees, where the ears are, more or less. All right, but for that sacrifice of not being able to see what's coming from behind at all, without moving our heads, what do we gain? We gain a lot of overlap forward from each eye. And what does that overlap give us? Depth of vision, what we call three-dimensional. So I can tell that that wall is not too close to me. It's not right up here. If I were only to look at it with one eye, you can close one eye. The mind, the kinesthetic sense has already supplied, because we're so accustomed to 3D that the mind supplies. But if we only will look with one eye, it's flat. It's really flat. There is no depth. All right, unless we move. If we move, yes, we can detect depth. But without moving, it's really just a flat surface that we're seeing. Because to see three-dimensionally, to see real depth, right? Not imaginary depth, but real depth, the two eyes need to overlap. The two sides need to overlap to give us a little bit of depth, to give us what is known as the vanishing point, which is also a thing that is studied in engineering and architecture. When you look down railroad track, where do they meet? They meet what we would call in the middle. It's called that's called the vanishing point. Actually, has a technical name, and we say that they meet actually in infinity, because we know that the rail tracks, strictly speaking, really speaking, are parallel, so they don't really meet ever, right? But the eye, because of the distance, puts them together there at that vanishing point, which is kind of a it's a illusory black hole, if you will, where everything goes into. And it really is a mathematical point, as it's defined single dimension, one dimension. All right, so the eyes are very much forward, precisely to give us depth of vision. That is a tremendous advantage in evolution, to have depth of vision. We sacrifice it for the back. However, so we're meant to really literally move forward, all right? And that even has we also projected mentally and even philosophically. We tend to project into the future rather than into the past. And we're always thinking forward. What am I going to do next? And in fact, to the disadvantage of reflecting on what's past in our lives is kind of an effort, and it's a burden to reflect on the past. You know, we're forward thinking, forward moving, forward projecting. So you can see there's a compatibility between the physiological, the psychological, and even the spiritual, because the ultimate at the spiritual level, the ultimate moving forward is what? Is eternal life, is the beatific vision, is where, at least according to belief, where we will be for all eternity. All right, so that's a really big forward. Anyway, back to the senses. You notice then that also the medium is different, going back to the fish and the human, because we both move, both the fish and the human, we both move in a fluid system. You notice they're both fluids, but what are the fluids? For the fish, the fluid is what? Water, fresh, salt water, brackish, I don't care how much salt you add or detract, but it's water and it's a fluid, right? And what is our fluid? Air, which is also a fluid, but it's a much thinner fluid. It's not as dense. And so what happens in water looking forward? Is there a lot of depth of vision in water? Not much. If you've ever done scuba diving or snorkeling, or, you know, there's not much depth of vision precisely because of the density of the water, number one. Number two, because all the stuff that's in the water, even microscopically, it starts adding up. So there's not much depth of vision in the water. Therefore, stereoscopic vision, which is what it's called, I was looking for the name, stereoscopic vision, which is overlap depth of vision, is not too useful for the fish because they're going to run out of sight anyway. They're going to run out of stuff to see pretty nearby, all right? In contrast, because air is so thin, we can see, and like the sound, like the song says, or the movie, on a clear day we can see forever, right? We can really see for miles and miles and miles, and on top of a mountain we can see out to the horizon even as it's curving. We cannot really see any further than that. Once the horizon is curving, we're actually looking at the curvature of the planet, right? And so that's as far as we can literally see physically before we go into space. All right, so depth of vision also is kind of restricted or conditioned, I would say conditioned by the medium which we move. So air is definitely an advantage for, or predisposes depth of vision in contrast to water. Now, we say that then sound is kind of a second, close second, as far as the senses, right? Information to sight. But our ears, we notice, are laterally, pretty much laterally. So we can actually hear stuff coming from behind. Not as well as we can hear from the front. In fact, we can hear best really laterally, but there is some overlap, and that's also what gives you that famous stereo sound, the stereoscopic sound, right? Again, if we are at a concert, for example, we can tell that the drum section is kind of on the left and the strings are up front, and then the metal instruments are maybe on the right, etc. So it gives us also location, where the sound, the origin of the sound. Now that's important also for survival. Think in terms of survival, because we're trying to trace the origin of human species as a whole, and the big environmental stressor, right? It's going to be survival, as we saw with Darwin very briefly, survival of the fittest, right? Genetic fitness, which then is expressed in a body. So that wraparound sound is an evolutionary advantage, right? Because at least we can tell where the tiger is coming from if we hear the roar. We could also tell a little bit the distance. If it's a faint roar or it's a very close roar, it would make a difference how fast I need to run. All right, so the wraparound sound is an advantage, and that's why the ears are lateral instead of forward or just backward, because we want to get that 360-degree cover all around us, at least with sound, right? And typically harsh sounds or abrupt sounds or sudden sounds are dangerous sounds, like lightning or roar or a kaboom from a big tree falling or from a rifle, okay? So harsh sounds are an alert. They put us on alert. And it's kind of, again, it's a kinesthetic reaction, but it's almost on the automatic. That a little segue here, that's why I say music should not be harsh. Because harsh music, what does it do? It actually gives us the wrong stimulus, right? It doesn't soothe us, it puts us on alert. So, I mean, I get enough alerts during the day already without having to be extra alerted with harsh music. Just a general appeal for trying to look for harmonic music. Harmonic music that actually soothes us and encourages our mind to go into those alpha waves that are more relaxing and allow us to think better and profit more from the energy that we're spending in thinking, right? So music should be harmonious as harmonious as possible and totally away from something that is disruptive and harsh. Just a comment. Anyway, going beyond then, so those I would say are the two, also the two senses that reach out at a distance, because the other three senses are basically closer up. Now there's a transition, right? Which would be the third sense that is generally close up, but also can pick up at a distance, which would be that the third sense. Well, touch, we can't really pick up at a distance, right? That's kind of the closest one. Smell. Now you notice, smell, again, there's no magic here. What has to be in the air for us to smell? A scent, yeah, but a scent physically or chemically, there has to be a chemical. There has to be a chemical that is somehow volatile, that is in the air, that is in the gas state. All right, so even liquids and solids are chemicals, but we don't smell them until we get very close up. And even when we get close up, it's because that solid or liquid is giving off some molecules into the air. All right, so a smell depends on chemicals floating in the air somehow. And that takes time. So smell generally is for close up. And when we look at it functionally, when we look at it in an evolutionary sense, it has a lot to do with, again, survival, trying to detect whether the food is edible or not. Okay, so there are some poignant smells. Again, that raises an alarm. For most normal people with a normal nose, poignant smells are not attractive, are not appealing. All right, it's a warning signal. Whereas pleasant smells may attract, not necessarily, sometimes for food, especially if it's cooked, right? So cooked food generally gives off good smell, and that's a characteristic, because think about it. What other animal do you know that cooks their food? Zero, okay? Again, functionally, in evolutionary terms, what did cooking do for primitive humans? Way back for the Flintstones. It started digestion. It pre-digested the food. It started breaking down mostly the carbon bonds, which are tough. They're covalent bonds. Takes a lot of energy, relatively a lot of ATP, say, and enzymes to break it down. Keep in mind, proteins, what's the pH of the stomach, approximately? About 1.5, no, that's like, yeah, it's like concentrated sulfuric acid. If I pour concentrated sulfuric acid on this table, first it's going to start smoking and then it's going to go through the table. All right, and that's the normal pH of our gastric juices. That's when those gastric juices come up through the valve with the esophagus. We get what is known as heartburn, right? It is burn, but it's not the heart at all. It's the esophagus that's burning because it's being digested by the gastric juices in the stomach. So milk and stuff like that tries to neutralize it, a buffer to neutralize that acid, but it's very acidic. And so cooking food pre-digests the food, it starts breaking it down. At the same time, look at the synergy, how interesting, it makes it pleasant in the smell in general, right? Other smells like perfumes and cologne and stuff like that have less to do with eating, have more to do with mating, all right? So pheromones and attractive smells used in mating. So we go back to the primitive state, that's where it was, the normal musk of animals, how they identify each other, especially mammals. And that's why many mammals go around signaling their territory, especially the male or the female, and that's how they track and trace each other. And it's very much species specific, at least outside this wall and outside the window, all right, in nature. We are very unique in many senses, how we have evolved, very, very sophisticated. We'll get to that eventually. All right, so then we talked about smell. Then we have what is left really up close is the last two senses, which are, right, touch and taste, right? For taste, it's kind of an extension of the smell. And in fact, they're associated, taste and smell are associated somewhat, right? Smelling good food and tasting good food is when we get a cold, which generally affects what system? The respiratory system, and therefore smelling, olfactory. We don't smell the food, and we also lose some of the taste of the food. So they're associated. Taste and smell, I think, I'm not sure, but I think they go in similar areas of the lobe of the brain where taste and smell are detected, and there's some overlap there. All right. So taste and smell are associated, but they're detecting a little different. So you can think of taste functionally as complementing smell, because in smell, we need the molecules to be in the air. But with taste, the molecules can actually be in the liquid or the solid, right? So it complements, it covers the three states. Right? So I can smell the steak, but I could also taste the steak. All right. Okay. And then finally, touch, which you notice, it's an actual system. So touch is embedded within a system. It's one of the systems of the body. Anyone know what is the name of that system scientifically? Like we got respiratory, circulatory, nervous. The nervous system is embedded into this other system, but it has a name. And I tell you, the word is similar. So you notice that the touch covers a whole body, right? A whole body, the head and the rest of the body. And it's on the very outside of the body. It's kind of the wrapping of the body, all right? And it gives external integrity, just like the nervous system gives internal integrity to the body. The touch system gives external integrity to the body. So anything beyond the touch is not my body, it's the environment. Okay, but anything inside touch is my body. So it's called integumentary system. And it's an actual system. So, you know, we talked about integration. We talked about the hierarchy of integration of from cell to system. Did we talk about from cell to organism? Okay, what is the basis of life? The basic unit of life. Cell is the basic unit of life, all right? If the cell is alive, there's life there, organically speaking, and so forth. Cells that have similar function, they come together to form tissues. Tissues with similar functions form organs. Organs with similar function form systems or organ systems, right? And then the last jump, so if I have, let's say, the body has anywhere between half a dozen to a full dozen organ systems, depending how we classify them. We classify them anatomically, or functionally. So for example, if we classify them anatomically, the skeletal system is different from the muscular system, right? Anatomically, they're made of somewhat different substances. But if we classify them functionally, we can talk about the skeletal muscular system, skeletal-muscular system. So functionally, they're one system because they function together. A skeleton without muscles is useless, and muscles, skeletal muscles without the skeleton is also useless, right? Okay. Anyway, so let's say we have about a dozen organ systems. If I were to lay out the dozen organ systems of an individual human being here, intact, the full nervous system, the whole digestive system, the whole respiratory system, etc. Do I have a functioning organism? Obviously not. They have to be integrated. They have to be working together, but they're different systems. So again, think about it a little bit. I'm still trying to get those neurons working, but up until organ system, we have been integrating things of similar function. So cells of similar function form tissues. Tissues of similar function form organs. Organs of similar function form systems. But then systems of different functions are integrated to form the organism, the actual living organism. So definitely the circulatory system does not do what the muscular system does, and does not do what the nervous system does, and does not do what the skeletal system does, etc. But they are integrated. And they function as a whole, as a functional whole, all right? What holds that back together functionally is the integumentary system. And what holds that back together internally is the nervous system, all right? And physically, you can, in our mind's eye, we can travel through human body, and we can see the skin on the outside, but we can see with our mind's eye, the nervous system, how it starts with the head and radiates out to the whole body, all the way out to the skin, right? And in the skin, we even have different types of nerve cells. So certainly if I prick myself or pinch myself, we have pain nerve endings, but we also have some other nerve endings. We have hot nerve endings. We have cold nerve endings, which are different. So we can feel hot and cold at the same time, right? Hold some ice cubes while take a warm shower, for example, and you'll feel both temperatures at the same time. We also feel pain and so forth. There are other nerve endings that are more subtle, right? But that's all part of the nervous system. That is also part of the skin system. There are also sweat glands in the system. There are hairs, for example, that project out, that keeps our warm, that makes us warm-bodied or warm-blooded. But at the base of each hair inside the skin, embedded in, is a hair follicle. And that follicle also attached to a little tiny muscle, okay? And that muscle is actually called the erector pilus. One erector pilus, several erecti pili. Okay, here's the Latin. And that erector pilus is the one that erects the hair when we get our hairs on end, either because it's too cold or because we get scared or whatever when the hair goes up, right? And you get a little bump. That bump is a contracted erector pilus. It's contracted, just like when we contract a muscle, we get a bump. All right, little tiny bumps, that's made from this guy, the goosebumps. The picture says 1,000 words. So it's so interesting to study the skin. First of all, it has several layers. Look at that, all the stuff that's embedded. There's the erector pilus. Bigger. This guy here. All right, and when it contracts, it makes a bump, and that's the goose bump. It stands the hair on end, literally. And look at all this gland, all the stuff that's involved. It's got capillaries to feed it, keep it alive. It's got sebaceous glands, sweat and fat to pour out and keep the skin. Even the skin has the three basic layers, right? The epidermis on the outside, then the dermis on the inside, and then the adipose tissue, and then all this conjunctive tissue in the between and so forth. A lot of stem cells in there, by the way, especially in the adipose tissue. And there's the outermost layer of our skin, very outermost layer of our skin is dead skin. So we're shedding dead skin all the time. When we shower and we use that scrub or whatever, we're peeling off dead layers of skin that are very important to have there because that's the first defense of the generalized immune system. It's the first defense against bacteria and fungi and everything else that's flying around, okay? All the insults that could hurt us, including chemicals, everything else. There are also sweat glands and oil glands. In other words, it's a pretty complex system, even though this layer is kind of microscopic. Maybe it has 1, 2, 3 millimeters, okay? But it's pretty complex. So it's a whole system that's involved here. And you see how it integrates the others. You have muscles, so that's part of the muscular system, circulatory system, etc. Okay, anyway, all this to say that this middle world that we live in is the world of the senses, okay? And it's normally what we can perceive with our senses plainly, without the aid of instruments. But there are two other worlds that we are immersed in simultaneously. We're just normally not very aware of them unless we are, for example, a microbiologist or we are an astrophysicist, okay? So microbiologists are always looking at microscopic stuff. What we can no longer see with plain sight, which comes down to about maybe 1 millimeter or maybe 0.5 millimeter or something like that. 1 millimeter is kind of the thickness of our nail, okay? 1 centimeter is about the depth of the width of our fingernail. 1 millimeter is kind of the thickness of our fingernail. When it starts getting smaller than that, we lose sight, all right? We may still have some touch, but not much. So the senses give off generally when we go into the microscopic world, except for molecules that we can smell or taste, but that's very close up. So, but when we go into the microscopic world, it's a whole universe. It's a whole universe in there, and the distances are proportional. Between atoms and molecules, the distances between those things are proportional to the distances between galaxies, for example, in the universe, when we put them to size, all right, when we put them in proportion. So it's a whole universe, really, that is the microscopic universe. In fact, when the microscope was invented little by little with lenses and so forth, Leeuwenhoek and Robert Hooke and all these people in the 17th, 18th century, Europe started getting more and more sophisticated instruments. They were fascinated by the universe of microscopic organisms they were discovering. And they were doing things as simple as like swabbing. Toothbrushes were not around at the time, so at best people would use like a swab or a cloth or something to wipe their teeth off, all right? And so they would swab the teeth of people, right? And they would look at that under the microscope and they would see millions of microorganisms crawling around. And it was fascinating. At the other end of scale, what I'm calling the super macroscopic would be beyond our Earth into the solar system, and the size becomes so large that we really lose sight, all right? Without instrumentation, we lose sight. For example, at night, on a clear night, moonless, we look at the sky and we see stars, right? We see stars. And generally, you can classify them into 2 categories according to their brightness and size. Some look kind of large and bright. Others look very faint and dim, tiny. So if we, again, just being very simplistic, we classify the stars at night, on a cloudless night, without moon, so there's no much reflection from the light of the moon, right? We see stars in generally two categories, the big bright ones and the small tiny ones. Well, technically speaking, what is the closest star to us? The sun, right? What we call the sun. So stars are suns. And we have one sun, it's one star. There's a one-to-one relation between one sun and one star. And we say, oh, look at the stars. It's a starry night. Remember, I think it was, who was it? Starry Night. That's a bit of a song. Okay, right. So the big ones are actually what? They're planets. They're planets, so they're not luminous bodies. Okay, so a light bulb. Remember when we used to have light bulbs? Okay, so a light bulb, when it's off, it's an opaque body. It's not luminous. When the light bulb is on, it becomes luminous, right? But when the light bulb is off, it's there physically, but it's not giving off any light. It's actually absorbing light. We can see the light bulb as long as some light bounces off of it. But a light bulb at night that is off, we cannot see. Unless we shine a flashlight, then we see the bulb. So what I'm trying to say is that the planets we see, not because of they're giving off their own light, but because light is bouncing off of them. And what is the light that is bouncing off the planets? The sun, our sun, all right? So the planets are receiving sunlight, and it means that when we see a planet, it's day. We can say that it's day on that planet, what we call the day. All right, even though it's night for us. Okay, so the big ones are actually planets, therefore they're not stars. They're opaque bodies. How about the small ones? Generally, the small ones are actually entire galaxies. Okay, entire galaxies. Entire galaxies. And what is a galaxy? How many suns? So we belong to one galaxy. What's the name of our galaxy? The Milky Way, right? The Milky Way. So look at this. On a moonless night, come on. No, not gonna work. Well, you can see these more or less, all right? So on a moonless night, these are photos taken with cameras, not telescopes. So we can see these if we're privileged to be in the middle of the Rocky Mountains on a moonless night and no clouds around. That's the Milky Way. That's why it's called Milky Way, because it looks like a whole. These are thousands and thousands, millions, trillions of suns, of solar systems. Maybe billions. I don't know if it goes up to trillions, but at least billions of solar systems just like us in one galaxy. Okay, one galaxy. Now, oh, yes, there is technology. You've heard about the Hubble. Now you've heard about the Webb, James Webb with 2 Bs, right? The James Webb telescope was sent out there. It's taking photos. Each one of these dots is actually a galaxy. And there are trillions of galaxies, right? Where's here? Trillions and trillions of galaxies. Look at that. Each one of these dots is an actual galaxy. So the dots, the stars that we see on the starry night are not at all. The big ones are planets, and the small ones are gazillions of suns of actual stars, right? But they're so far away that we see them as a point. And that's another experiment that can be done, which at night on a flat terrain, it takes 3 people, or you can do it with 2 people. One is the observer. Let's say we're the observer and our partner is facing us with 2 flashlights. Let's say the partner puts the flashlight out like this, on, facing us. So if the other person is nearby, we definitely see 2 lights, right? Now the person has to walk backwards, so it's better if he puts the flashlights looking backward and he can walk forward. Or she can do that, gotta walk, and then they gotta walk in the darkness. But as that other person walks away from us, shining the two flashlights at us, what do we see just conceptually, as if it were a single plane? We see those two dots, those two light dots actually coming together. They're also getting smaller with the distance, but they're actually coming together, which they're not, because it's not that with walking, the partner's arms are shrinking, right? The partner's arms are not shrinking. He's not doing this, or she's not doing this, freaking us out. No, they're keeping the flashlights at the same distance, but walking away. If that person walks away far enough, those two dots will merge into one, if it's far enough, okay? And so it's an optical illusion, but the reality is still there of the light. That's the same thing that happens with the stars, with the little stars that we see. Anyway, that super microscopic world is there, and it's a huge, humongous universe, and it's measured in such large quantities that it's difficult to wrap our mind around those quantities. All right, I'm going to move forward. So we can look at three big origins: the origin of the universe, the origin of life, and the origin of humans. The first one we already talked about in the environmental bioethics course with the Big Bang and all that. So I'm going to give a summary here, and Elizabeth, you'll pick up on this when you get the other in the environmental course, basically. But we know that the origin of the universe is approximately 14 billion years ago. 14 billion. Okay, now scientific notation is very convenient. You know how in science we're obsessed about numbers, measuring everything, and we're also obsessed about crunching stuff, compacting. So it's much easier to write 10 to the 9 than to write a 1 and 9 zeros, right? So the exponent is the number of zeros, don't get confused. When we say 10 to the 9, how many individual digits are there going to be? How many individual digits is what I'm saying. Where's my board? Here. Okay. So we say 10 caret, that little thing is called a caret, to the 9, right? Is equal to a 1, and then how many zeros? 9 zeros. Okay. So everybody agree? So how many individual digits do we have in this number? We have 10 digits, all right? Because it's 10 to the 9, it's not 1 to the 9, which would always be 1. All right, so the 9 means the number of zeros that we add beyond the individual unit. So when we say 5 times 10 to the 9, that's equal to what? 5 billion. All right, just a little review from high school, which we reviewed also in college and now in graduate school. People get confused, all right? Because the 1 times 5 is 5. All right, so scientific notation is very useful because it crunches a huge number into an exponent, basically a base, and this is base 10, which is also the basis for the metric system, right? Metric system in increments, so we could talk about orders of magnitude. First order of magnitude is 1, second order is 10, third order is 100, 1,000, and so forth. And you can also do that with a decimal point into smaller orders of magnitude, larger or smaller, okay? Orders of magnitude. All right, so origin of the universe about 14 billion years ago. Here's another abbreviation, another acronym, BYA, billion years ago. Sometimes you see it in uppercase, sometimes lowercase, etc. The Earth itself, within the universe, is fairly recent. It's in the past 4.5 billion years. which is pretty much the origin of our solar system, the sun and its planets. The 4 inner planets, the 4 outer planets, and then the 4 microplanets also that are circling around. Okay. So 4.5 billion years, more or less. And we just throw that number, you know, we say 4.5 BYA. But that's a humongous number. That's a humongous amount of time, amount of years. So I do this little exercise. Let me see if I have it here. If, oh, it's not going to let me do it in Excel. Anyway, if we do an exercise, do that on your own. Okay, I'll leave you a little homework there just for fun to exercise the neurons. If we count to 1 million, how long will it take to count to 1 million? One by one. All right. Well, first we have to set some conditions for the experiment so that we make it kind of even. Because if we say we start just 1, 2, 3, 4, 5, and look at the clock, you know, by what time we get to 999,999, well, it takes much longer to say that, right, than to say 1. So we have to, let's say, even out the playing field. How do we even out the playing field? Well, we just give a value to each number, a time value. So how can we uniformalize counting numbers that are so diverse, like from 1 to 999,099? Okay, well, we can do that conceptually and even mathematically just by assigning a time value to each number, regardless of what the number is, number X. All right, and I'm going to say, for the sake of simplicity again, so that it matches the clock, right? How we used to counting time is, let's say that we assign 1 second per number, or 1 number per second, 1 number per second. So what does that mean? That in 1 minute, how many numbers do I count? 60 numbers. So it's easy enough. All right. So basically the math would go like this. I cannot use an Excel because of the technical difficulty here, which I'll resolve at some point. But so we're counting the number. The question is, how long does it take to count to 1 million? All right. Well, if we assign that value, we uniformalize our counting system. We say that it would be 60 numbers, or rather, let me say this, from 1 to 60 in 1 minute. Does that work? That's the standard. All right, now we can go forward from there. So 60 is 1 minute times 60 to get to 1 hour. So we can do that operation easily. How much is that? 6 times 6? Quickly, 36. And how many zeros? All right. Then we'll multiply that number times what to get 1 day. How many hours in a day? We could probably do that also. Let's not do it. That's cheap. But it's just a basic operation, right? So at least we'll go there. 36,000 times 24. Okay. 86,400. I should memorize that number. So in 1 day, counting every second, all right? Counting every second, I will get to what number? 86,000. Only 86,000. In 1 day, counting continuously, no sleep, no eat, no nothing, no bathroom, just keep counting. Well, maybe you can count in the bathroom, but just keep counting. It will take 24 hours straight just to get to 86,000, you know? So you do the next operation, which could probably be a division actually, right? To get to 1 million, how many days? Counting straight, how many days will it take to count to 1 million? All right. Then, how many more days, or maybe weeks or months, will it take to count to 1 billion? would be the second question. All right. So those are the two homeworks. Let's see some actual numbers next time. Okay, so this number billion is so large that we don't even agree on what to call it. Because there's the American billion and there's a European billion, and those are two different quantities. So in scientific notation, okay, so 1 billion is how many zeros? Right? And so it's 10 to the what? 9. But that's American. It turns out that this, for the Europeans, this is 1,000 million. It's not a billion, it's 1,000 million. For the European, a billion is a million million. So it's 10 to the what? A million millions. How many zeros? 1 million has 6 zeros. A million million is going to have another 6 zeros, right? This is the next order of magnitude up, the next grouping. Which is what? 10 to the? Yep. And that's the European. Billion. Okay. So this number is so huge that we haven't even agreed on what to call it. And therefore, the scientific notation is universal, because if I say 10 to the 9, I'm not saying 10 to the 12 and vice versa. And so in real scientific journals and articles and so forth, communication, you'll find scientific notation. Okay. And only in popular writing will you see the billion thrown around. But so when I say this 10 billion year, this is an American billion. All right, it's 10 to the 9, 13 times 10 to the 9, or 4.5 times 10 to the 9, really. So that's this little exercise here. This is wrong. It's not 4 or 5 hours. All right, I don't want to belabor the point, but oh yes, another one is light years. So this is a reference to time, right? This is a reference to time. So the origin of the universe with the Big Bang and all that. And this can be, how can we know this? We can know this, we can infer it from a real phenomenon that is out there that is called the background radiation. I don't know, did we talk about background radiation? When we looked at, yeah. This background radiation is supposed to be, according to astrophysicists, what is left over from the Big Bang, the explosion. Just like, for example, if there's an explosion now, you know, with something, a cracker, a firecracker, or whatever, there's going to be some leftover, right? There's going to be the residue of the firecracker itself and so forth. You can scale it up to an atomic bomb. There's certainly going to be residue, including nuclear activity, radioactivity. Well, the same with this. That is the biggest bang that has occurred, as far as we know, in the universe. And it has left residue, which is this energy that is called background radiation. And because it's energy, energy can be measured, right? It's not spiritual. Energy is real. What's the type of energy? What's an example of energy? You're all using it right now. Electrical energy. And that's not magic. If I put my finger into the socket, I know it's real. Okay. So there's light energy, electrical energy, heat energy, electromagnetic energy. So there's all kinds of energy. That is segue into the next little thing that we're going to see, the mass energy equivalency. But this background radiation, which you can see has been colorized, of course, for purpose of being able to see it, right? It can be measured and the intensity, and that's how they can extrapolate that when this was a single point, it must have been about 14 billion years ago, or 10 to the 9. Okay. So that's how that origin is measured. I'm not going to elaborate too much. Yes, please,
Well,
Kenny.
Is it like, is it heat energy that's coming off, or?
I don't know exactly. It's yeah. It's radiation. So it's some kind of a wave energy. All right. But I don't know. Your question is very good because heat energy fits into what we call entropy, which is energy that dissipates into the universe and is no longer available for work. That's how we define entropy, or heat energy that dissipates out, but it radiates. So this issue of radiating is interesting, okay? The radiator, precisely because it goes in all directions. For example, the energy from the sun that we get, which is radiated energy, the photons, which is the light energy, it radiates out in all directions. However, the sun is so large that for practical purposes, so you notice that radiation, radial energy, they're not parallel rays. They're not parallel, right? Because they're radiating from a focus, from a center, out, right? So they're precisely radial is not parallel by definition. However, for practical purposes, the light energy that comes from the sun, for practical purposes, is considered that the sun rays are coming in parallel, because that surface, the surface of the sun, is so huge compared to our surface that for all practical purposes, it's like a little dot. Earth is a little dot here, and the surface of the sun is so huge that for all practical purposes, at the local level, is practically parallel. We have something similar with gravity on Earth. Okay, gravity on Earth. Technically, so is gravity a parallel energy or a radial energy? It's radial because it's going to the center of the Earth. But we cannot really get to the center of the Earth, right? But it's going there. We assume it's there, that the center of gravity is at the center of the Earth. And so what makes this drop is gravity, right? If I drop another object that is not at the same spot, okay, hope it doesn't break. You could think that these are going parallel, but they're only going parallel at the local level. Within the whole system, they're actually going radially, right? Because they're going toward the center of it. So they're only falling, we can say it's an approximation. If we measure the distance between these two objects, and we measure the distance where they fall down here, even at the level of microns, it's probably the same distance. But when we get down into Armstrong units or something like that, or 10 to the minus 10 or 20, we'll see that this distance is slightly shorter than this distance up here, because they're actually falling radially. I'm exaggerating, they're doing this, right? So at the local level, yes, they fell parallel, but that's an approximation. That's not real. Real is that they really fell in a radial sense. And if I had an instrument that was sophisticated enough, I could measure the difference between the two distances. Yeah. And by measuring the difference between those two, I can also measure, estimate the velocity or the time or vice versa, back and forth, play with the formula. Okay. Anyway, so back to radiation. I don't know if the background radiation is actually heat, but it radiates as heat. Okay. Heat will become important when we see that Earth gives up heat. We absorb light, and then there's an energy transformation when it goes through the system of the Earth. And we don't give off light, except the artificial light of the cities. You see those pictures of satellites at night into the city. That's artificial. Natural, we don't give off natural light. That's why we're all peak body, right? Well, we do give off heat radiation. All right, let's continue here. So that's the, oh yeah, so the other one that I want to cover here a little bit is the famous Einstein formula for mass energy equivalency. This is called the matter or mass energy and equivalency. Actually, mass is better than matter. So capital E stands for energy. This is again a convention among physicists and scientists in general. So capital E generally is for energy. M is for mass. We talked about mass, right? Mass is the resistance to change. How do we get the weight? When we weigh ourselves, we talk about the weight on the scale. When we weigh ourselves on the scale that is in the bathroom or somewhere else in the house, what do we actually weigh? The number that we get is actually the mass. All right, the mass. And how do we get the weight? We'll multiply that mass times gravity. In other words, the scale is simply ignoring gravity. But gravity is 9.8 meters per second squared. It's an acceleration. Gravity is an acceleration, right? You know the difference between velocity and acceleration. We talk about speed, but if we are at 55 miles an hour on autopilot, the car, is that acceleration? That's not acceleration. It's constant speed, right? So it's velocity. But if we accelerate on the ramp or decelerate to get out, then it's a change in speed. Okay, it's a change in velocity. That's acceleration or deceleration, which is a negative acceleration. All right, so gravity is a type of, it exerts acceleration. If we multiply the mass times the gravity, then we get our real weight. And so let's say that we weigh on the scale, what's your favorite weight? 140, 120, all right? We multiply that times gravity, which on the surface of the Earth is 9.8 meters per second square, right? What Newton gave us, rounded up to 10 meters per second square to make the math simple. 150 times, okay, 120 times 10 is how much? 1,200. 120 times 10 is 1,000. That's your real weight. Okay, so we weigh much more than what the scale is saying. We weigh 10 times more. All right, so stick with mass and ignore gravity. And that's why on the moon, do we have less mass? It's the same body, so we have the same mass, but we weigh less because the moon exerts less gravity. It's a smaller body, so it exerts less gravity. So there's a proportion between the mass of the body and its gravity. And by the way, while I'm on this, all masses exert gravity. All masses exert gravity in the smallest mass. It's just that the gravity that is of anything on the Earth is the mass of anything that's on Earth is so much smaller than the Earth itself that the gravity of the Earth overwhelms every other gravity. But if I had two objects, two balls, right? Try to make them as heavy as possible, let's say lead or something like that, two heavy balls that are perfectly spherical, and you put them an inch apart, in a few hundred or million years, they're going to be half an inch apart. They actually attract each other, but they have to compensate for the friction. They have to overcome the friction of gravity that is pulling them down, you know, and it's a force that is perpendicular to their mutual attraction. But they will, with time, overcome it, and they will come together. It's very slowly, right? Because everybody exerts gravity. It's just like the gravity of the Earth, the mass of the Earth is so much massive than anything else on Earth that it kind of overwhelms. That gravity overwhelms every other gravity. But that's the mass here, okay? Then C, lowercase c again. What is lowercase c? Stands for what? It's the uppermost speed on the universe. It's kind of also known as the universal constant. C is speed of light, right? One photon, which is approximately how much? 100,000 kilometers per second, or less. Check it out. Speed of light, kilometers. 300, sorry. Yeah. Not working with it. 300, sorry. My bad. Okay. Now let's think about this for a moment. Again, we're looking at magnitudes, orders of magnitude. We already established that the distance of the universe is immense, right? But now we want to see, the time. Oh yes, because I want to get to also what is called a light year. Light year. I'll write it here. And I'm going to put year in quotations just to emphasize that it's not real time what we're measuring, but rather distance. All right, so let's say that hypothetically we all have a photon between our fingers, which is a particle of light, right? And we release a photon. Where will that photon be in 1 second? How much will 1 second? Remember when I used to play flag football, we'd have to count 5 Mississippis right before we can rush the line. And so we go 1 Mississippi, which is supposed to be 1 second, 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi. All right. So in 1 Mississippi, that photon would be how far away? We all have a photon on our finger, between our fingers, and we let go, we release a photon. 300,000 kilometers away. Forget about the curvature of the earth, forget about gravity for now. This is a hypothetical experiment. It's what Einstein used to do, thought experiments. We get into a lab in his brain and we do experiments, okay? So we release a photon, it will go in a straight line, because speed, velocity, all right? It will be 300,000 kilometers away in 1 second, even before we actually say the word photon. In 2 seconds, it will be 600,000 kilometers away. Again, before 4 seconds, it will be 1 million kilometers away. Another insanity. And that's the speed of light. That's the real speed of light. And that's supposed to be the upper bound speed of the universe. That's why it's known as the universal speed. But recently, I read a little article. I just skimmed through it about this particle that they have discovered apparently that goes faster than the speed of light. I didn't have time to get into it, but I want to look at that because that was an eye opener for me. Anyway, that's C, all right? Lowercase c, caret 2. So square that number. Meaning three, well, in scientific notation, times 10 to the, just a straight up speed of what? 10 to the what? 300,000? 10 to the? 6 would be 1 million, no? So it's a total of 6 digits, but how many zeros? 5, 10 to the 5. But we're squaring that, which means what? Caret 2, right? And what do we do? Multiplying exponents to what? Exactly. So it's 3 times 10 to the 10. Do that math. That's the speed of light. All right. Sorry, that's the formula. That's the constant here. That's the universal constant. So whatever mass multiplied times that humongous quantity gives us the energy of the mass. It's bewildering. This whole mental exercise, just to say that a little tiny mass contains how much energy? A humongous amount of energy. And that is basically the basis for atomic energy. That is the basis for a nuclear bomb, and that is the basis for a nuclear reactor lighting up an entire city. A little tiny mass contains a humongous amount of energy within it. Again, it's amazing because mass is all over the place. Of course, the more massive bodies, right, the more dense bodies are going to have more energy stored in them. And when we look at the table of elements, what are going to be the more massive bodies, the more dense bodies are the ones with more protons and electrons, okay, like uranium, the more, and those tend to be, they have more isotopes, and they tend to be more radioactive. And those are the preferred elements for making nuclear reactions, whether a nuclear bomb or a nuclear reactor to light up a whole city, okay? And so that was the genius of Einstein coming upon this truth, right? This magical truth, and that's why it's called mass energy equivalency. This is what allowed the research on nuclear stuff that is done today. And it started pretty much during the Second World War, because both the Germans and the Allied forces were after the nuclear bomb. Okay. Okay, I'm not going to say more about that now because it digresses too far. Going a little bit more into physics here for the moment, just to establish that Einstein had spent the last years of his life on a quest for a unified theory of all forces, of the four fundamental forces, and without success, okay? And not too many scientists are pursuing that today, but some groups are. And as far as I know, they haven't been able to come up with a single unit force yet. This has to be done mathematically and then proved experimentally, which is a challenge, because you know, theoretical physics and theoretical whatever goes faster, moves faster than the experimental stuff, because the experimental, we need the technology to get there. And sometimes we can think of things without being able to test them yet, like E = mc squared. Eventually that was tested and proved to be true, all right? So these are the four fundamental forces on Earth, in the universe, that we can detect. Two are known as attractions, and the other two are known as fields. So the two attractions are at the microscopic level, and the fields are at the macro and super macroscopic world. That's why I introduced that terminology, because when we think about them, we're really not too aware of them, at least the two attractions in the microscopic world, but they're holding atoms and molecules together, okay? Because the strong force is the force that holds the nucleus together, the nucleus of an atom. In other words, protons together. Think about this. What is the charge of a proton? Charge, not mass. The three alternatives: positive, negative, neutral. Positive proton, right? And therefore the orbiting electron is negative. And then another subatomic particle that is in the nucleus, the neutron has zero or no charge, but it does have mass. That's why it's in the nucleus. All right. So protons are positive. And from child's play with magnets, remember how we all play with magnets, right? What attracts what and what repels what? And that's why they're called that way. There's such a convention. We could have called it yellow and purple, but we call it positive and negative. Because in our minds, conceptually, positive is opposed to negative, right? Anything. So what are the, what two forces attract and what two forces repel? Or what force repels what? Positive and negative attract each other. Remember playing with little magnets? Don't tell me you never play with little magnets. Okay. All right. So positive and negative attract each other, right? Much more than gravity, faster. And therefore, positive and positive. Remember pushing the magnet with the other magnet away without touching it, right? Because those are the two positive poles. Now take that to the molecular, take that to the atomic level. Protons are positive, they're all positive. In the nucleus of an atom, which is the basic unit of what? Not the basic unit of life. Some people get confused the cell with an atom. They're both basic units, but of different categories. Yes, the cell is the basic unit of life, but a cell is made up of trillions of molecules and trillions and trillions of atoms within, right? But the atom is the basic unit of matter that is stable because we have subatomic particles, but they're not stable on their own. They fly around like electrons, protons, and neutrons. But when they come together to coalesce into a particular element, then they stabilize. All right, so protons are in the nucleus and they're all positive. Why are they not flying out away from each other? Yes, by what? The what? No one really knows exactly, but they've actually worked out formulas. We're getting into what is known as quantum mechanics, right? Or the standard model of the atom by Niels Bohr and followers. This was all elucidated about 100 years ago, at the beginning of the 1900s. The standard model of the atom, right? Protons and neutrons, and then electron at the nucleus, and then the electrons orbiting. What is keeping those protons together? The strong force. We could have called it serendipity, we could have called it Gromoldsky, whatever, but we call it strong force because it's very strong. It's extremely strong just by Einstein. So you see the relevance of Einstein's formula, E equal mc squared. The smallest m is an atom and is the strongest force at the micro level, at the microscopic level, right? So what about the weak force then? By definition, the weak is going to be weaker than strong. So there's a noun and there's an adjective, right? They're both forces and they're also known as attractions. But the weak force, by definition, is much weaker. And that's the one of the decay, the isotopic decay, what makes isotopes of the same element. Different isotopes, if we change the number of protons, do we keep the same element? High school chemistry, right? Periodic table, there it is. If we change the number of protons, what do? Change the element. We go from one element to the other, starting with what's the smallest element possible? Hydrogen, because it has how many protons? 1, and so on and so forth, right? Okay, so we don't change the number of protons, but what can we change? The number of neutrons. Generally, the number of electrons will match the protons, but the number of neutrons, we can add or subtract neutrons because they don't have a charge, but they're making the same element heavier or lighter, all right? So you ever heard about heavy water? Heavy water is actually radioactive water, and normal hydrogen has how many neutrons? Normal hydrogen is a 1-to-1 relationship. The normal one generally is the same number of protons and neutrons. So for hydrogen, how many neutrons? 1, normal one. But hydrogen can also have 2 neutrons. It's an isotope, right? In fact, hydrogen has 3 isotopes. So normal, and then deuterium. Ever heard the word deuterium? Deuterium is a 2-neutron hydrogen, right? Here's that Latin again, deu, twice, all right? And tritium somehow, therium is somehow a reference to atom, the T atom, therium. So deuterium is a hydrogen atom with 2 neutrons instead of 1. Not as stable, it will tend to lose that extra neutron, fly out. And then there is a third isotope. I mentioned isotope. I mentioned tritium. Tritium has how many? What's your guess? 3, right? So it has 3 neutrons. You think that's very stable? Not too many, not too stable. So that third neutron tends to fly out. And when they fly, that's what we call nuclear decay. If it flies out, that atom will become deuterium. And if it loses the other one, it will become normal hydrogen. Okay? So the thing, what is holding that neutron in place is the weak force. It's the weak force because it can release, and that is also known as the half-life. Every element has a half-life, right? When half the mass of that element loses its neutrons and decays to half the weight or half the mass. Okay? Half the mass, not the weight, sorry. But it can be weight, and that's how we get at the half-life. Every element has a half-life. So the weak force is basically the isotopic decay, but still at the nuclear level, at the atomic level. So they're super, super small forces, but in the range, they rule. They rule, okay? And that's essentially what is keeping the atom stable as the basic unit of matter. We cannot get any smaller than that, having stable matter. If we go into unstable states, yes, there's much more. Even the subatomic particles are, now it's known that they're made up of other smaller particles yet. Anyone know what are the components of neutrons and protons and electrons? Because they, once they thought, it was thought that those were the smallest particles possible. But now it's known that even those particles are made up of even smaller things. Generally, here we're again into quantum mechanics and all that. They're called quarks. Ever heard the word quark? Yeah, because they behave very quarkly. You know, a quark is something that you can't really get a grasp of. All right, quarks. They have funny names like top quark and bottom quark, and they have flavor and stuff like that. It gets weird. All right, so these two forces are at the atomic level, at the microscopic level for sure. Again, I mentioned attractions because of that positive, negative stuff. Whereas the other two are in the macro and super macroscopic worlds. Gravity, I've talked about already, we'll experience it, etc., etc. But gravity is a weak force. It's a very weak force. When you start getting away from the center, it dissipates and it becomes so weak that at some point it loses its effect. So it's definitely in relation to distance, right? But gravity is a very, very weak force compared to the others. Electromagnetism, again, is different in this sense that you notice it's a compound word held together by a hyphen, all right? So it's got electricity and magnetism at the same time. At first, these were thought to be two different forces. But it turns out that a magnetic field generates electricity and an electrical field generates a magnetic field also. So they are now linked together as a single force, which is called electromagnetic. But the funny thing about it is that they are in, they are in perpendicular direction. They exert their force in a perpendicular way to each other. Make it very graphic. For example, if I have a cable here, a metal cable, let's make it a nice conductor like a copper cable, all right? And I run electricity through that cable. To have an electrical force going through is the electricity moving through, right? It's the electrons moving through the cable. So I have electrical force going through, okay? But at the same time, that cable becomes magnetized. In other words, it develops a magnetic field around it. That is kind of an invisible casing that is magnetic. It magnetizes the cable. All right. But that force, that magnetic force, is perpendicular to the electron travel through the cable. It's perpendicular. And that's a magnetic. So a magnetic field and vice versa. These electrical generators, right, is a magnetic field is created with magnets, and then a rotor is put inside. And when the magnetic field is energized, it will make the rotor turn. You think of positive, negative, positive, negative, positive, negative. I can make that motor turn, right? The rotor, and by turning, it generates electricity. It can generate electricity. So it can go back and forth. So that's why it's lumped into a single force, electromagnetic, and it's a field. All right, well, enough about the four fundamental forces. Is just to remind us that these are the first two are at the macroscopic level. The other two are mostly at the macro and super macroscopic level. And for example, they keep the planets in orbit and so forth, and the galactic systems. So we're very much subject to them, but we're not thinking about them on a daily basis. Now, I'm just putting this number out for now. We'll come visit it again when we look at the origin of life and the experiments of the Mueller-Urey experiment, recreating the primitive atmosphere and how to start getting organic compounds from the primitive atmosphere with chemical reactions. Again, no magic, no fantasy, real organic stuff, real material stuff occurring in chemical reactions. So I'm going to put this number out there about 4 billion years ago, more or less, American billions. Then a review, I'm going to do this quickly because it happens that this course happens to have a solid scientific background. So remember, organic molecules need carbon and hydrogen, all right, both. Of course, we can classify all molecules or compounds into organic and inorganic, right? What makes life is really a mixture of these two types of molecules, but the organic molecules specifically are the ones that are responsible for metabolism, which is life at the chemical level within the cell. That's why we say that the cell is the basic unit of life, because the cell in situ, in its place, can metabolize. All right, so for example, CO2. Is CO2 an organic, CO2 a molecule, first of all? Made up of atoms, right? There are stable CO2. There's CO2 right now in the atmosphere. We're producing CO2, we're exhaling CO2, small amount of it. So it's real here in the air. Is that an organic molecule, CO2? It's exhaled by human beings. It's exhaled by living things, cellular respiration, right? Is it itself an organic molecule? Well, it's got carbon, CO2. Where's the hydrogen? CO2 is not an organic molecule. It's a product of metabolism, but CO2 is not an organic molecule, period. Another one that is basic for life. How about water? Think of water. Without water, no life, right? Because inside the cell, again, that metabolism is occurring in a soupy environment. We are 85, 90% water. Is water an organic molecule? H2O, where's the carbon? Nowhere. So water, as vital as it is for life, is not an organic molecule. Anyway, that's just to set the record straight. But the organic molecules are classified into 4 main categories, 4 main groups, remember? Carbohydrates, lipids, proteins, and amino acids, or nucleic acids. Sorry, not amino acids, nucleic acids. All right, so give me an example of carbs, carbohydrates.
Bread.
Yeah, what's in the bread itself is made out of
Glucose.
Yeah, well, that's sweet bread, but the bigger molecule, which is many glucose put together, and sucrose and fructose and all these, starch, right? So starch. It's a carbohydrate. It's a huge molecule, Glucose is a smaller molecule, but it's also the sugars. So starch, sugar, all that, those are carbs. Cellulose, which is the main component of plants. Cellulose is also, so anything that with also see glucose, fructose, galactose, right? Cellulose, that OSE ending is typically a carbohydrate. Right? Lipids are fats, what else? Oils, waxes, another one, fats, oils, waxes. So the fourth group there will come to me. All right, so they're hydrophobic. What does that mean, hydrophobic? They don't like water. They don't mix in water. They don't dissolve in water. Phobia is an aversion to hydro, reference to water, hydrophobic, aversion to water, right? As opposed to something that mixes in water, like for example, salt, or hydrophilic, right? Philia is love. Philadelphia is a city of love, so they like. All right. You have to use your imagination to see Philadelphia as a city of love. I lived there for a while. Okay. Okay, proteins. Examples of proteins at the macro level. A lot of proteins in nature, right? Animal protein, muscle tissue. Plant protein, legumes, beans. That's at the macro level. They have animal protein and plant protein. We break it down. Proteins are made up of polypeptides, and polypeptides are made up of amino acids, right? 20 amino acids in nature. They will become relevant with the Miller-Urey experiment. So the basic, say, functional units or stable units of proteins are these amino acids. They're in nature, they're in food, and that's why we need to digest proteins. We need to break it down to amino acids, and then that will be absorbed by the intestines into the circulatory system, et cetera, et cetera. Some proteins are structural, others are functional. An example of functional proteins, we have thousands of them in our bodies. They basically manage metabolism. Enzymes, right? Enzymes, they speed up chemical reactions. And then finally, nucleic acids. It's a little more technical, if you will. People in general are less familiar with nucleic acids in that terminology, but they include the two large categories of DNA and RNA, okay? A lot of people know the acronyms, fewer people know what the acronyms stand for. So let's start with a simple one. RNA stands for ribonucleic acid, right? There's the acid, ribonucleic acid. Again, just basic terminology, ribonucleic acid, RNA, capitals, caps, I'm just being lazy. And so DNA, you build up on this. The D is deoxyribo, et cetera, et cetera. And it's DNA. Well, let me not be that lazy. All right, deoxy. So it means that it has less oxygen inside. It's in the ribose ring, the ribose ring of the nucleotides that is missing an oxygen, and that makes it deoxyribonucleic acid. It's a big difference. A little change makes a big difference, because generally, which of these two molecules is more stable? Structurally, the DNA is much more stable because it's a double helix, right? So the two rungs stabilize each other with a twisted ladder that everybody's familiar with. Twisted ladder, rungs, the double helix, that's the DNA. Whereas RNA generally is single-stranded, and so it tends to hairpin upon itself and wiggle around, and It's much less stable. Also, there are many more types of RNA than DNA. There's, for example, messenger RNA. There's ribosomal RNA. There's transcript RNA, transcription RNA, etc. Single nucleotide RNAs, etc., etc. Okay, many different types of RNA. In fact, it's called the RNA world, and they do different functions inside the cell. And so it is thought that before we got to the DNA world that we have today as a molecule of inheritance, there was an RNA world, precursor, because there are many more varieties of RNA than there are of DNA. It's an inference, okay? It's an inference from thinking, analyzing what's available today and going back to roots. We'll have more to say about that again when we look at the origin of life, organic life on Earth. But anyway, those are the nucleic acids, right? And all of these are known as macromolecules because in contrast with like CO2 and H2O, for example, how many atoms in one molecule of CO2? Quickly, 3. How many atoms in one molecule of water? 3. So those are very tiny molecules. These macromolecules have minimally thousands and typically millions of atoms, and sometimes trillions of atoms. When you think of a single DNA molecule, one DNA molecule, if I pull out from one cell in the form of chromatin, not distinct chromosomes, but in the chromatin form, that is like a single spaghetti strand, all right, from one single cell, from one single nucleus of a cell. If I pull out one DNA molecule and stretch it out here in front of us, how long is it going to be? Not miles, okay, but meters. It's about 2 meters long. It's about 2 of these. All right, one single molecule. Imagine the gazillion atoms on that thing. All right, so they're generally known as macromolecules. And that's a level of chemical complexity that occurs in what we say metabolism. So again, that single word metabolism involves a tremendous amount of complexity. But even metabolism itself can be broken up into 2 types. Building up molecules is called anabolism, and breaking down molecules is called catabolism. We'll get to that, not to worry about it. We'll get to it. All right, moving forward. This is very, very basic. Just we use the metric system for measuring temperature. So Celsius or centigrade, same thing. Celsius is the guy who invented it. Fahrenheit is a different measurement. It's not metric, and the equivalence, as you can see, 0 centigrade is 32 Fahrenheit. Just for, again, for setting the record straight, 100 centigrade is 212. This is not a minus. This is 200, it's just a dash. 212 Fahrenheit, okay? If the room temperature right now is about 70, probably it's getting into the 60s. 212 is a very hot area, the temperature. And what do these mark from 0 to 100 in the centigrade? What do these 2 amounts? What do this caloric content, heat, what do they mark? The state of what? Water, pure water, going from what to what? At 0, vice versa, right? And liquid to gas. Liquid to gas, exactly. No, because there is a phenomenon that where it goes to solid, from solid to gas, it does, and it's called sublimation, and it occurs with snow naturally, right? Yeah, it skips the liquid phase, but it's not at normal pressure. It's high up in the mountains where it's much less pressure. So remember the pressure, the temperature pressure laws, the gas laws, what's called gas law. Again, a lot of this high school physics and chemistry review. But there is that phenomenon of sublimation in chemistry is when snow goes directly into water vapor, into cloud, without passing the liquid phase. but it's with much less pressure high up in the mountains. Okay, when there's less atmosphere and less gravity, it's like. All right, anyway, that's so this is what establishes the metric system in liquids or in temperature using pure water as the standard at sea level pressure, at sea level, because if we change the pressure, also that's going to change. The primitive atmosphere, I bring it up because we're going to look at it again when we talk about the origin of life with this experiment that was done in the 50s to simulate the primitive atmosphere and give it an electrical shock, simulating lightning, and see what came out of that, which was very interesting. So a primitive atmosphere had mostly, it was very different from our atmosphere. It was totally toxic for us today, right? In fact, it's estimated that the atmosphere has changed about 4 times drastically. And we're on the 4th iteration, which is benevolent, which has enough oxygen to breathe and very, very little of the other gases that are very toxic. Like, for example, ammonia and methane, and even hydrogen, which is highly explosive. And there's a very tiny, it's a fraction, 0.% of hydrogen in the atmosphere. All right. And it's a good thing. Otherwise, our atmosphere would just be totally explosive and not livable. The numbers here should be subscripts. All right. Just pardon my laziness. All these numbers, the numbers should be subscripts, and they apply to the previous elements. Right. So you notice of these, which is how many organic compounds here on that list? Just one. All right. Methane, which is a gas. All right. And it's a gas of digestion. That's one way. And it's a gas also of putrefaction, of rotting. It's a rotting gas, right? So methane and propane and butane and all those. So it ends in ANE. Typically, it's an organic gas and it's flammable. And it's also a greenhouse gas. In fact, it holds, I think it's about 40 times more heat than CO2. So thanks to God, there's very little methane in the atmosphere, but it's increasing. And that's also a concern for global warming. And like I mentioned, hydrogen is very explosive. Ammonia is a byproduct of metabolism and is eliminated typically with urine. And in fact, it's the N, the nitrogen, that makes urine yellowish, because nitrogen is yellowish in color in nature. But it's a product of metabolism, but it's not an organic gas. It's an organic molecule. About actual definition of species, we saw that with Meyer already, so no problem there. Scientific, do we see scientific classification? Yeah, it's just a recap. Species, genus, family, order, class, phylum, kingdom, domain. We saw that already. Yeah. Okay. Origin of humans. Here we have this is the big origin that we're really going to devote the rest of the course to, right? The tribe, which is a category in between family and genus. Should be aware of that now. There are in-between categories that are used for purposes of classification, but they're rather technical and you don't hear about them too much. For example, there are supra and sub. We hear about vertebrates, right? What are the 5 categories of vertebrates? Animals with a segmented spinal cord, right? So mammals, birds, reptiles, amphibians, and fish. Those are the 5 groups, 5 classes of vertebrates. But vertebrate itself, vertebrata, so these are 5 classes. What's above class is phylum. But vertebrate is not a phylum, it's a subphylum. The actual phylum is chordata or chordates, that they have a cord, all right? A spinal cord or a notochord, a swimming cord, etc. So what I'm saying is that there are categories that are supra and sub, like in the case of vertebrate, it's a subphylum. Also, there are other categories, especially in the primates and the hominids, that are known as tribes and clans and so forth. Tribe is one that is in between family and genus, right? Between family and genus is tribe. And this tribe of the hominin is what we're after with the origins. That's like the first origin of truly humans. That's where we get Homo, hominin. So Homo is a genus of the tribe hominin. They emerged. I'm giving you the synopsis here. We'll go into more detail in the following lectures, but this tribe of hominin is thought to have emerged about 8 million years ago, according to the fossil record, mostly fossil record, right? Fossilized bones, mineralized bones that now are like rock hard. Then, but the hominin also include the chimp-like branch, which are troglodytes. For example, the pan, P-A-N is the genus of the chimpanzee today. We diverged, or the Homo diverged from the chimps about 6 million years ago, or I should not say chimps, but the precursor of the chimp, right? The common ancestor about 6 million years ago. And the genus Homo as such, at the level of genus, about 3 million years ago, between 2 and 3 million years. Modern man, I'm giving you here the synopsis, modern man about 200,000 years ago, 200,000. What does this mean? If we were to look at a primitive human, man or woman, from about 200,000 years ago back, back thousands of years, about 200,000 years ago, we were to look at them, give them a good wash, clothe them, we would not distinguish them from any human walking the streets today. That's what we call anatomically modern human, anatomically modern, okay? And so this notion, this fantasy of cave people, cave men and women, as primitive, someone with long hair all over the body and stuff like that, and hunching over, that's a fantasy. That's not real, and it's not sustained by the fossil record. Rather, if we go look at the fossils of humans about 200,000 years ago, they will look exactly like us. But if we go further back, like 300,000-400,000 years ago, the level of Homo, right? Different species, they look similar, but not exactly. They start looking more primitive-like, and more, I'm going to say, monkey-like. All right. But we have to go further back. And here I've listed at least 6, depending on how they're classified, maybe from half a dozen to a full dozen of different Homo species that are in the fossil record, but are extinct. All right, it's like saying, okay, well, give me a name of one cat species by their common name. The cats, the Felidae, the family of Felidae, right? The felines. A lion is one, another one in a different continent. How about India? Bengal tiger, right? How about North America? Yeah. How about Florida? The Florida panther. Okay. So these are all different species, all right? But the same genus, the same family. It's like saying, well, now there's only of all these cats, now all the other cats, and there's only the Bengal tiger left. All the other cats have disappeared. They're extinct. Something kind of similar to that. All right. We're the only one species of the genus Homo, but we have fossil record that we cannot deny that has been discovered of at least half a dozen and maybe up to a full dozen, depending on how they're classified, because we're classifying bones, right? And sometimes we only have a fragment, we don't have a full skeleton. let alone an entire population. So we're going on very skimpy data. That's called a paucity. Paucity is a reference to poverty, the paucity of the fossil record. So this is a phrase that Meyer uses and many others today, anthropology and so forth. The paucity is the poverty, very little. You know, I'm going to infer soda cans from one can of soda that I found years ago that is all rusted and corroded. And I'm saying, therefore, I deduced that all sodas were bottled in this can, this type of can, a cylinder made out of aluminum, just from one rusty old can that I found somewhere. Okay? Paucity of the fossil record. Still, we work with that. And we do, so we go into the probabilistic world and we do percentage of probability or how the cranium will look, more or less 3 or 4%, right? Based on this fossil. The characteristics for the human, at least at the level of Homo, okay, at the level of genus, fully bipedal. And think of the consequences, it frees up the hands. For what? For making tools. The brain is at least twice the size of contemporaries. Again, and the closest contemporary from the DNA is the chimp. Actually, I think our brain is about 3 times the size of a modern chimp. Just brain capacity, or actually the cranial capacity. Also, we harness fire. We domesticate fire, if you will. So it's no longer a threat. We actually use fire for many things. Think of the steam engine, boiling water to run machines. Only species that wears clothing, right? Unless it's your pet dog in the middle of the winter, buy him a coat. Lithic, lithos is a reference to stone, lithos. So lithic technology is using stones as tools and making tools. For one thing is to use a tool, another thing is to make a tool that makes a tool. Symbolic culture, but highly sophisticated, including religion. Again, we don't see animals. Animals do rituals. Animals can be ritualistic. What's the typical ritual of animals? The mating ritual, right? There are other rituals that are not mating, maybe laterally associated. Scare ritual, like when a lion roars, okay? So it's to, most animals don't really fight, they just freak each other out and see who can freak each other the strongest, and they win. They don't actually have to get into the battle. And there's ritualistic battles also for territory, etc. But to the level of transcendental, not. Transcendental meaning actually symbolic language to kind of represent what's metaphysical, what's beyond this physical reality, like an afterlife, including burying the dead. Again, we don't see any other animal really truly burying the dead or burying them clothed, and even with food. What does that tell us? That there is some kind of a belief in an afterlife. Got to feed the fellow going into the afterlife, making the transition, right? We don't see any of that. We don't see tombs for any other animal. And the most primitive human cultures that have been discovered, they all have tombs. So another human characteristic. When we get into the soul, then that's another layer of complexity. That's where we need to introduce philosophy and theology, which will be in the second half of the course. All right. Then this one is supposed to be into Meyer, but it's already almost noon. So how about we take a 10-minute break here? And then I'll just go briefly over chapter 1 of Meyer. You've read it, so we'll talk about it briefly. So I have 11:55, and we'll come back at 12:05. All right, deal. Here we go. Pausing recording. Resume recording. I want to talk a little bit about Meyer. I don't want to see a show of hands or anything, but I hope you've been reading it. Okay. We're not going to cover the whole book, but at least the first several chapters. And talked a little bit about Meyer already. He lived over 100 years, so he covered the whole 20th century, basically. I think he was born at 1904 or something like that, and died in 2005. And he wrote this book when it was in the 90s. All right. So we can think of it as kind of a summary. We have the benefit of a whole lifetime of research and thought. Very meticulous, very thorough thinker. He was involved in the modern synthesis, as I mentioned early on, bringing evolution and genetics together, and also gives us, so he's a population biologist, and he gives us the definition, the biological definition of species that is still very relevant today, even though today there are other definitions of species that are more ecological, like taking the group of animals or plants or whatever looking at in context of the rest of the environment. But the biological definition, I like it, it's very practical. So a species doesn't know that it is a species, right? Like a lizard doesn't know it's a lizard and so forth. But we use classification, we use taxonomy, so that we identify the individuals within that group and say something intelligible about them and use them for purpose of study and communicate with each other with a scientific name, which again, it's interesting. Linnaeus, Carolus Linnaeus, this Swedish guy who invented that taxonomy, right, goes back about 300 years. And imagine your paradigm to last for 300 years. Nowhere in sight to be changed. The names of species, sometimes we reclassify species when we find out more genetics about them or their DNA. But the classification as such, to have the species contain the genus, for example, like we say Homo sapiens or Felix domesticus or Canis lupus, etc., that paradigm still sticks and into the future for who knows how long. So it's pretty neat to have a paradigm that one invented to last for so many centuries, right? And still be very useful. Anyway, what I like about Meyer also is that, so the biological definition of species, you see me going back, referring to that, it's important to maintain the two necessary conditions in mind, all right? Because there are going to be exceptions. And what are those two definitions, two conditions? According to the biological definition of species that Meyer gave us, Ernst Mayr, what are the two conditions? These individuals, I look at a number of organisms. They look similar, they look alike, they have the same number of, the same feathers, the same pattern of feathers, and so on and so forth. I see there's male and female. Then to classify them as a species, are all these individuals belonging to the same species? Two conditions, right? Remember? They need to be able to interbreed, right? And then produce offspring that are fertile. So it goes to the next generation. In other words, really, when you think about it functionally, I always tell my students, think functionally. That will put you ahead because we don't see functions, we see structures, right? But think functionally. What does it mean to produce fertile offspring? That I won't know until that offspring actually reproduces. So first, the offspring has to become an adult, which is the definition, the biological definition of adult is capable of reproduction. So the reproductive organs have to mature, produce fertile gametes and so forth, and then the actual reproduction occur. And then I can say, therefore, its parent belongs to the same species because their offspring are fertile. All right, so you see, it's kind of how to say that it's a retrograde thing. It's hindsight. In hindsight, that we can say these species, these individuals belong to the same species. All right, but it's very practical because I can test that. can see, well, are they producing offspring? Yes, good. They're mating. Now, are the offspring fertile? Good. Okay, so it's the same species or not. But then I say there are exceptions. And one typical exception is what we call a hybrid. What's a hybrid? A hybrid is two different species, but are related species. For example, the typical hybrid that is used a lot is a mule, right? A mule is a donkey and a horse, male or female on either side, but will produce this mule. However, typically hybrids generally are infertile. They live, a mule lives and eats and plows the field and whatever, but typically they're infertile, they're sterile. Okay, so we can see that hybrids can occur, but they tend to be dead ends. However, there are exceptions, and some can be fertile, right? Anyone know what is a liger? Heard of a liger? It's a lion and a tiger, right? And typically, also in general, at least in mammals, the hybrids tend to be larger. So mules tend to be larger than a horse and a donkey, which is their parent. So they have that ability to, they're stronger because they're bigger, more bones and so forth. And the ligers tend to be larger than either a tiger or a lion. But they have a pattern that's in between. They can have stripes, and they also have a mane, right? Like the male lion. But do those happen naturally? Generally, hybrids don't happen naturally because a horse is not going to recognize a donkey as another self to mate with. You know, they'll smell different, they have different anatomy and so forth, so they don't really mix with each other. You see horses over here and donkeys over here, and you don't see them interbreeding naturally. How about a lion and a tiger? Same thing. I mean, they're not even in the same continent, right? Because lions are African and tigers are Indian. And there's a Himalaya in between. It's the largest mountain range in the world. So naturally, these two different species don't mix. In fact, you can push that argument even further, that even different populations of the same species many times don't mix. So this gets me into the population, right? Because Meyer is going to define evolution at the level of population, which is, again, it's a little conceptual, you know, and to this day it's an argument at what level, what is the smallest level that evolution occurs? Is it at the level of the individual or is it at the level of the population? Because by definition, a population is what? It's not a single individual. It's two or more individuals, and typically a larger number, right? It could be thousands, it could be millions in the sense of bacteria, for example. And so he maintains it's really at the level of population, okay, which is made up of a few or a lot of individuals, but of the same species. However, we can have populations of the same species living in different areas, like different geographical regions. And those are two different populations of the same species. When they're brought together artificially or by some kind of natural migration, they may or may not intermix. It depends, because they may look exactly identical to us, like a band of zebra over here and another band of zebra, the same species over there. They come together to a third place, which is a new grassland, for example. These two populations may have developed pheromones or some other chemicals that they don't like to make, they don't smell not correctly for each other's population. That could be the beginning of speciation, when two populations of the same species, two different populations of the same species, they begin to not recognize each other as same. All right, that could be the beginning, could be, but see, we're going to a probabilistic world here because it doesn't mean that they necessarily have to end up in speciation, but it allows for the possibility. So anyway, so another thing that I like about Meyer that you don't see too much anymore is a hardcore scientist getting into philosophy and even theology. Okay, and that's where I want to pick up, because I try to teach this as an integral fashion. Certainly, I'm going to introduce, because at least from the believer perspective, there's that apparent dichotomy between creation and evolution, to the point that many people in society today, if they're believers, they have to reject evolution. And if they're believe in evolution or they understand evolution occurring, then they have to neglect or discard their faith, which I'm saying is not at all. Because what I'm trying to do throughout the whole course is to present the evidence that far from being opposite to each other, they actually complement each other, creation and evolution, those two narratives, they complement each other, but at different levels. All right, so Meyer does that. However, I'm also going to say that he's a much better scientist than he's a philosopher or theologian. And I don't know for a fact, but I suspect that at least from this book, reading this book and his critique on religion specifically, is that he did not have a systematic background, or at least as systematic in theology and religion as he did in science and empirical science. Okay. So there's one chapter there that you can read it if you want to, but I don't require it. At least I don't require a summary because it's not that good. And I'll give you my critique of that. All right. So he starts by looking at big questions, right? Big questions. And he concludes the big questions of who we are, where we're going, where we came from. Where we came from. There's the origins. And what about the world, the universe? Well, I talked about 3 worlds and so forth, and origins there too. So those are big questions. And he says, in general, he uses this word mythological in a kind of restricted way because mythology in that it is pre-scientific and it's not based precisely on the scientific method. Quickly, the scientific method, observation and experimentation, right? In between, we develop a hypothesis, then we test a hypothesis to see if it matches reality and so forth. So it's not rigor, discipline, method as in the scientific method, right? So pre-scientific answers to these big questions. He crunches it down to 3 possible alternatives, which are the infinite world of Greek philosophy and everything cycles just by observing nature in a strictly non-scientific way. What I mean scientific is modern science, because there was some kind of primitive science, if you will, going on, that there was some discipline of thought. But basically, this modern science begins about 500 years ago with the Copernican revolution, right? Nicholas Copernicus changing from geocentric to heliocentric, that the universe is not spinning around the earth, that rather the universe is spinning around the sun. It's closer to reality, but it's not reality itself, because it happens that our planetary system, including our sun, is embedded into the Milky Way, but it's embedded in one of the long arms of that Milky Way pattern of striation, what is that called, a spiral. And even as far as we know, the Milky Way itself is not really at the center of the universe. In fact, when I talk to a few astrophysicists and people like that, center for the universe doesn't make any sense. It is expanding, but it's expanding in every direction, proved by the Hubble telescope and then confirmed now by Webb. So it doesn't make sense for modern cosmology to talk about a center of the universe. It's a different realm. Okay, again, it gets weird. Let's bring it back to Earth. He talks about these 3 alternatives of this recycling world from, say, classical Greece, about 300 to 500 years before the time of Christ, or the alternative, which is the biblical narrative of creation, that is rather short, and God created everything that is kind of in a fixed state. So he created the giraffe as giraffe, and the hippopotamus as hippopotamus, and bacteria as bacteria, and humans as human, and so forth. And there was no place or space for evolution or cycling in in God's creation, right? In that narrative. So that typically comes from the Bible. Again, he's a product also of his own environment, just like we are. which was Germany and generally continental Europe of 100 years ago, okay? Which is mostly Christianity in general, some form of Christianity, either Catholicism or Protestant. Even the Orthodox Christian, which is that third branch, is in the East, more what is today Eastern Europe and Russia, etc. So he puts this out there as one of the possible alternatives and then proceeds to shoot it down as totally naive and unscientific. And then the third alternative is the world of evolution, or basically, Darwin's model, then complemented with Mendel's genetics. And that's the one that he obviously espouses. And he says is the one that is the real answer, the one that matches reality best. And then he proceeds to go into the whole issue of essentially the rise of modern, what we would say modern science or empirical science today. I mentioned again about 500 years ago with the Copernican revolution going forth. Then we have another figure, a French scientist who comes up, Lamarck, Jean-Baptiste Lamarck. And of course, he introduces this thing of what is the Lamarckian inheritance of acquired characteristics. There are these phrases that are symbolic and meaningful and full of power. Okay, so inheritance of acquired characteristics. Please correct my misspelling if you see any. All right. So, first of all, when I see phrases like this, I usually try to start from the back, from the end, because that's where typically the noun or the substance is. By the way, I kind of sprinkle philosophy and theology along the way as I go along, but the noun is a very important part of the phrase, right? Or the sentence. And what does the noun tell us? What part of a sentence? When I say to be human, right? What is the noun? To be human. Human is the noun. Again, I'm doing a lot of high school stuff that should have happened in high school, but just in case it didn't, and then it may or may not happen in college. The noun gives us the substance, the whatness. It answers the question, whatness, all right? And so in grammar, the noun is also known as a substantive, right? Which is the substance of the thing. Philosophically, the essence. So we are humans. That classifies us. And it's an inclusive and an exclusive category. It includes all humans and it excludes all non-humans. See how we go into philosophy for grammar? It's very important. So the characteristics, right, are accidents on the substance. In other words, the spots on a leopard, all right? So a spotted leopard, which is the noun? Leopard, and which is the adjective that qualifies the noun. You see, the adjective qualifies the noun. Spotted, green balloon, as opposed to, it's a red balloon, not a balloon. Yes, a red balloon is a balloon, but it's red. So it changes the accident, but it doesn't change the substance. All right? Doesn't change the substance. So the characteristics are various characteristics on the species themselves. And the classical example that was used by Lamarck and others in this inheritance of acquired characteristic is that how did the giraffe get its long neck? Example. By stretching, right? Well, giraffes do stretch, and what do they stretch for? Yes, and specifically, one of the few trees that is available in the African savanna where they live, all right, which is the acacia tree. There's different types of acacia, and there is, bang. So I didn't make this up. I didn't take this photograph. Okay, I didn't pre-plan of it, but it's classic. We see a giraffe definitely stretching out for the leaves of the acacia, which, by the way, this thing is full of thorns also up here. Have you ever seen the tongue of a giraffe? It's like sandpaper. I mean, it's a real tough thing, the tongue, because it has to go weed through here and pull out the leaves in the middle of thorns. Okay, that's a level of detail. But we see here that all the other leaves have got eaten up by other animals, maybe shorter giraffes or baby giraffes. And now the taller giraffes can reach out here. And it's definitely reaching, right? We see that poor fellow reaching out. If he had toes, it would be on its tippy toes. So that's obviously how the neck got that long. Well, wrong, because it's the inherited. It could be that this giraffe got a taller neck by stretching slightly taller. You know, at night we stretch out, and during the day we sink a little bit, maybe up to an inch. Have you ever noticed if you get into your car first thing in the morning, and you look at the rear view mirror, you can adjust a little bit, right, so that it's correct. You get into the same car late at night. You have to readjust the mirror a little bit, because now the mirror is off because we're a little shorter. And the mirror is looking higher than what we needed. So we need to adjust down that mirror. Well, then you get up the next morning early, you go back to the same car, you got to readjust the mirror a little bit because we stretched out overnight, maybe up to an inch, just by sleeping, by being horizontal as opposed to vertical. Anyway, that's a vertebral thing. But the point is that there is really no inheritance of acquired characteristics. Okay, the neck is an acquired characteristic, is there because the baby giraffe got its neck from its mom and dad giraffe, but it's not by stretching that the adult giraffe passed on the longer neck. Is that the giraffe was already born with the potential for longer neck and developed that longer neck during its lifetime as a group. But the genes were there. It's just that it wasn't known back 300 or 400 years ago that the mechanism of inheritance was the genes. Simple example for workout, okay? So the athletes and these hulks and the bodybuilders, the babies of bodybuilders are not born muscular. They're not baby bodybuilders, okay? They have the potential. Look kind of ugly, right? To see a bodybuilder baby. But they have the potential because but it's not because their parents were bodybuilders necessarily. It's because their parents had the potential for bodybuilding and they developed that potential. You know, other people who walk around skinny and not are not hulks, they maybe have the same potential. They just never developed that potential. Okay. But they have the same potential in principle because they belong to the same species. So overall, they have the same genes. That can be qualified a little bit with certain predispositions that are athletic or not, like a low pulse rate, but that's also genetically inherited, right? I don't develop a lower pulse rate unless I take some medication or chemicals to lower it. So there is no inheritance of acquired characteristics generally. However, the value of Lamarck by introducing this concept, right? What is the value? Is that at least he was thinking in terms of inheritance. At least he was thinking of change from one generation to the next, because before then, the basic thing was scala natura, right? Or the scala natura, or the ladder of life. Scala natura was pretty much static, and you cannot go from one rung to another. It was fixed. and everyone had their place. So even if we talk about a tree of life, I see all these diagrams and symbols and so forth, even if it's very complicated and so forth, it was fixed. Everybody was in a fixed place, every species, if you will, right? And there was no moving from one species to another. This is the one that is most classical, the Scala Natura, represented symbolically as a ladder, and each rung had a particular species, okay? Who do you see made up the tallest, the highest rung here? What species? The human. Yeah, today we call it egocentric, but when we looked around, we're definitely the most intelligent and the most capable. We can dominate other species, right? And therefore we must be at the top of the ladder. And there ain't no way that anyone else is coming near us because we're at the top. King of the hill. All right, so it's a very simplistic, primitive way, not very scientific way of looking at life, classifying it that way. So the value of Lamarck, if you will, of this inheritance is that at least he got people thinking in terms of change from one generation to the next, which is already kind of heretical for his time. Because he was going against the concept, the static concept of Scala Natura, that every species had a place in nature and so forth, and there was no movement from one place to another. Little bit kind of analogous to the caste system in some primitive societies that has caused really a lot of problem because they cannot move from one social status to the next, right? All right, so Darwin's bombshell, if you will, with The Origin of Species. By the way, here's a full title of the book, which is a natural sentence. The Origin of Species by means of natural selection. He's telling us the mechanism, but this mechanism is still a very general thing. What is natural selection? You know, it's a construct. It's just it's a selecting out of the weakest. Yes, it's a mechanism, right? But still, what is causing it at a deeper level? Or the preservation of favored races. Again, races today doesn't have a scientific basis to it. You can include here favored groups in the struggle for life, or favored organisms, right? In the struggle for life. That, when it was published, it was a bombshell because it was going against a lot of the standard of the time, the common belief and all this, and it seemed to go against the religious belief of creation. It seemed that it was denying the whole narrative of the book of Genesis, right? And when we talk about book of Genesis, it's a Judeo-Christian tradition. So what are you saying, Darwin, that for 5,000 years we have been wrong? Okay. How dare you, right? All right, so that was the perception. Again, the book was misinterpreted, but also the Judeo-Christian tradition was misinterpreted to be a creationist type of description, which I'm going to dismantle in the following lectures, right? This creationist view of scripture and tradition is superficial. It doesn't apply really when we do a rigorous analysis of the biblical text that we'll look at. Specifically, Genesis 1, the first book of the first chapter of the first book of the Bible. That whole narrative of creation, right? The 6 days of creation, the 7 days. All right. Moving forward, then, talking about entropy, yes, is a gradual decrease in the corridor, which typically is measured as heat that dissipates and is therefore not available for work. If we trap heat, we can make it work, right? Doing what, for example? The very typical thing is we trap heat, we use it for boiling water, and then the steam of the boiling water can move an engine and can generate electricity, for example, so on and so forth. So, but that's trapped heat. When heat is allowed to radiate out, it's lost into the universe and it cools down basically, and it's lost for work. So that inability to do work is known as entropy, and it increases disorder then, because it's not increasing order, then it must be increasing disorder. Life, as we know it, organic life, which is chemical reactions in an orderly fashion, goes against entropy, which is why would we have a system that goes against entropy and therefore allows for life? A little philosophical, but the question has a lot of merit, because if the general tendency, not only of our planet, but our solar system and the galaxies and the whole universe is this increase in disorder, this increase in entropy, why should there be life? Because it's diametrically opposed to that. And that's precisely by harnessing, if you will, heat, or harnessing chemical reactions at the smallest level, which is at the molecular level, in what we call cellular respiration. And the counterbalance of the same reaction in the opposite direction of cellular respiration, which is what? Instead of burning glucose, making glucose, photosynthesis. So the complementarity of those two reactions, basically, just think about it. It's actually one reaction in a different direction, right? If we go from water and CO2 to glucose through photosynthesis, we're making an organic compound. Two inorganic compounds combined make organic compound, glucose, which is the basic carbohydrate. When burned, the energy that is released allows the cell to work, recharging ATPs and all the metabolic processes, the cascades that occur at cellular level, at the tissue organ system level. Bingo, we have life. And it's amazing that one chemical reaction going in both ways allows for life on Earth. Incredible. It's just bewildering. But it's true. There it is. All right. I want to stop there. This is basically my summary of chapter 1. Try to integrate it into today's lecture and give me a single summary. All right. For those of you who are still in the summary process, and then we go from here. Questions, comments? No? All right. If I hear none, then I'm going to stop the recording. And thank you very much for being here. And God willing, we'll meet again next Saturday.